Hello and welcome back to our series on thermal management in semiconductor packaging. Today's lesson explores one of the most important tools in modern electronics design, thermal analysis and simulation. With increasing power densities and smaller footprints, effective heat management isn't just about design. It's about predicting and optimizing how heat will behave before a product is ever built. In this video, we'll walk through the why and how of thermal simulation. We'll start by reviewing essential thermal metrics like junction temperature and thermal resistance. Then, we'll cover different simulation techniques, including FEA, CFD, electrothermal code simulation, and PCB level modeling. We'll also talk about how simulation connects to the physical world through IR imaging, hardware in loop testing, and optimization. As chips become more powerful, predicting thermal behavior becomes more critical. Design teams can't afford to prototype their way through problems anymore. Instead, thermal simulation allows us to model the temperature behavior of semiconductor packages under real conditions, all before fabrication. Whether you're designing a heatsink, analyzing die attached materials, or trying to prevent delamination, simulation gives you a strategic advantage. Here you can see a heatsink simulation and a real engineering workstation running a thermal model, bringing design with analysis. Simulation has become the cornerstone of efficient thermal design. Physical testing can take weeks and cost thousands, especially when redesigns are needed. Simulation lets you do various things, such as visualizing temperature gradients, test boundary conditions, simulate extreme scenarios, and reduce the number of costly physical prototypes. On screen, you'll see a stress pattern in a chip under simulated thermal cycling and a curve showing how simulation can significantly reduce development time and cost. Every thermal analysis revolves around a few key numbers. Junction temperature, or TJ, is the highest internal temperature of the chip. Thermal resistant values like ROJA and ROJC tell us how efficiently heat moves from junction to ambient or junction to case. Other metrics, like delta T, help assess thermal gradients that can cause mechanical stress. The graphs here illustrate how junction temperature rises with power, and a thermal resistance breakdown shows where that heat is going. There are two primary approaches to simulation: analytical and numerical. Analytical modeling uses equations to estimate temperature rise. It's fast, but limited in accuracy. Numerical methods, like FEA, break geometry into smaller elements and solve detailed heat equations. You'll see a side by side view. One is a simplified analytical heat spreader model, the other is a full 3D mesh ready for FEA analysis. In most real projects, engineers use both methods. Quick estimates followed by detailed simulations for verification. FEA, or finite element analysis, is one of the most widely used thermal modeling tools. It breaks down the package into discrete thermal zones and solves temperature at each node. This helps us see where heat builds up, how it flows through materials, and where structural deformation might occur. In this image, the die attach, and mold compound are all represented in layers, each with unique thermal properties. On the right, you'll see the resulting heat map and areas of thermal expansion stress. CFD, or Computational Fluid Dynamics, focuses on heat convection and fluid flow. This is especially important for systems with active or passive airflow, like cooling fans, enclosures, or heat sinks. Here you can see airflow being modeled around a populated PCB and a CDF analysis of a heatsink. CFD helps designers identify dead zones where air doesn't flow or surfaces where temperature gradients exceed safe limits. It's crucial for system level cooling. Modern semiconductors don't just produce heat, their electrical behavior changes with temperature. Electrothermal co simulation allows designers to model how electric power changes affects thermal conditions, and vice versa. This is critical for high frequency, high efficiency switches like GAN and SiC transistors, which self heat rapidly. We show an image of co simulation results, while temperature and electrical current are computed together, allowing for dynamic feedback. PCB level simulation zooms out to consider how the printed circuit board itself conducts and dissipates heat. This includes copper traces, thermal vias, and group planes. A heat map illustrates how a poorly placed component can lead to localized overheating, while the second image shows how thermal vias distribute heat across board layers. This analysis is often done in tandem with ECAD tools, helping both layout and thermal teams collaborate. To truly understand heat flow, we need to simulate how the entire product enclosure interacts thermally with the package. That's where system level simulations come in, combining chip level thermal models with fans, enclosures, vents, and even environmental airflow. Here, we can see a control unit inside its casing, simulated with airflow vents and heatsink attachments. This type of integration helps prevent surprises during late stage testing and validates that packaging decisions work within the actual product design. Once simulations are complete, engineers turn to infrared imaging to validate their results. Thermal cameras detect real surface temperatures during operation, either verifying that the simulation was accurate or identifying missed hotspots. In the visual, you can see an IR image of a power board under test, side by side with the simulation. This loop of simulate, test, adjust is a gold standard in thermal engineering. Hardware in the loop, or HIL, takes things a step further by merging real electronics with simulated environments. It allows you to apply real power loads, thermal cycles, and monitor real time behavior, all while simulating the rest of the system. The HIL bench shows here monitors an automotive power module under real driving profiles with sensors tracking temperatures, fan speeds, and fault responses. This bridges the gap between software prediction and physical performance. Thermal simulation tools aren't just for analysis, they're also for design optimization. By running parametric sweeps, such as varying pad sizes, materials, or TIM properties, engineers can find the ideal configuration that minimizes temperature while meeting other constraints. A graph on the left shows how changing a single variable, like copper thickness, affects junction temperature. Another image on the right visualizes a simulation workflow that automates this process to find the best outcome. Now let's close with a few real world examples. In a SiC inverter module, thermal co-simulation was used to optimize gate driver layout and reduce hotspots. In another case, a data center AI chip used hybrid FEA and CFD to refine its cooling system before tapeout. Finally, PCB level simulation helped eliminate hotspots in a compact drone and control board, allowing higher power density without increasing board size. Each of these cases shows how thermal simulation transforms design from guesswork to engineering precision. Thermal analysis is no longer optional, it's an essential part of modern semiconductor packaging. From FEA and CFD to IR cameras and HIL benches, the tools we've explored today allow engineers to predict, test, and optimize how heat moves through a device. Simulation reduces cost, improves reliability, and accelerates innovation. As devices become more compact and powerful, the importance of thermal simulation will only continue to grow. Thank you for watching.